Hello, everyone. Welcome to another Connection Wednesdays after the summer break. Today, our topic is the optimization of timber column anchoring. Let me introduce myself. My name is Jana Kadirova. I'm a product engineer. And today I have two of my colleagues from IDEA StatiCa. It's Jan Valíček, our consultant, and Adam Kozoušek, our product engineers.
Hello.
So, and these two guys will lead you through the content of today's webinar. Before we start, one practical note, you are muted by default as usual. And if you want to ask some questions or send us some comment, please use the questions panel in GoToWebinar window. We will go through them during the webinar, and after the webinar, we will answer your questions if we have enough time. In case the webinar is too long, we will send our answers via email to you. So please use this panel and send your comments and questions. And what is the today customer's project? It's a very nice and interesting building by Czech engineering company TAROS NOVA. And more about this project will be presented by my colleague Jan, who is a former employee of this company. So he has very detailed information about the project, you will see. Before we start, please answer my first poll. And the question is, the design optimization is for me. Is it important because it saves money of mine and also of the employer, or it's important because it saves money to the client, or it's not important because you will not get paid for the additional work, or it's not important because the savings are insignificant? So please use this poll to let us know what do you think about optimization of the project. In case you have some technical issues with the voting, please try to maximize the window of the poll, because sometimes we have some technical issues and you are writing us that you cannot vote. Okay, I can see half of you have already voted, so I will leave you a few more seconds. I can see the results are quite clear. Okay, so I will close the poll now, and let's see the results. So 70% of you voted that it is really important because it saves money to the client, and the rest thinks that it saves money to the engineer and to the employer. Thank you very much. And now I will pass the presenter to Jan Valíček, who will show you more about the interesting project. So Jan, the floor is yours now.
Thank you very much, Jana. I hope you see my screen and my presentation.
Sorry, I will hide the poll. Okay.
Okay, can you see it?
Not yet. I cannot see the screen.
Okay, now?
Yeah.
Great. Thank you very much. So, hello, everyone. And I will introduce you the project, and also I will tell you a little bit about the company I worked before my career at IDEA StatiCa and other career steps. So the company who agreed to provide us the project is called TAROS NOVA from Czech Republic, from the beautiful town of Rožnov pod Radoštěm. And TAROS provides complex services in timber and steel structures. They are focused on really tough and non-standard structures, mainly from timber, glulam, steel, and also like hybrid structures. Their main or highlights are like timber towers and skywalks. They also do many swimming pools, sport halls, like non-standard playgrounds and very complex houses. They operate internationally as well. So if you are interested in what they do, you need some contact and advice from them, you can contact them directly. You can see their web page. So once more, again, thank you very much, Taros, for sharing the project with us. So now the project itself, it's kind of special for me because actually I was the engineer of the project. So I know, I would say, everything about the structure, the structural engineering and the detailing of this project. When I worked for Taros, it was actually 6 years ago when this project was designed. So it's called Aquarena, and it's located in city of Samorin in Slovakia. It's close to Bratislava, the capital of Slovakia. It's about 20 kilometers of the Bratislava, next to the Danube River. Very nice place. And it's a part of a huge complex of sports and leisure facilities, X-Bionic Sphere. Here you can see the aerial view of the whole site, and our aqua arena is here, the swimming pool. There is also like external swimming pool. There is a athletic track here. There are also like many facilities for equestrian sports. So if you like horses, it's right place for you. Also nice restaurant. So if you will be there nearby, I recommend you a short visit, have a lunch, have a short break, take your kids. It's a very nice place to spend a day. So let's move on to the structure itself. The structure is made of glulam frames. The layout of the swimming pool hall is approximately 55 by 37 meters, and the height of the main timber structure is 11.1 meters. The structure consists of 12 two-pin portal frames, as I said, made of glued laminated timber. The bracing is provided by timber struts and steel rods. There are also some non-standard members or elements. Here in the gable wall, there is a timber truss to reduce vertical deflection for the glazing. And there is also a small water slide tower. It's made of cross-laminated timber panels. So if you will be there and you like water slides, you will see the structure more in detail. Here you can see the plan of the hall. So 12 frames, four bracings, and some other parts. Here's the typical section of the hall. So you can see the shape of the frame. This is the part without bracing, and we will focus on the anchoring here. You can also see the assembly joint here. It was due to the transportation limits. It consists of 3 parts: this column, the short column here, and the main beam in the middle. There are also like steel parts to fix the struts, timber purlins. It has a quite lightweight build-up of the roof. Okay. So now I will tell you something about my original design of the anchoring of the footing. Here's a snap from the 3D model. I used the software RFM for the global analysis, and I've got the reactions. I've got the vertical force of 385 kilonewtons. I also, as I said, the structure is quite lightweight, and there was also an uplift of 19 kilonewtons. The horizontal force was 150 kilonewtons, and the lateral force in the anchoring was 80 kilonewtons. This 80 kilonewtons was only in parts with bracing. Here we will focus on the anchoring without bracing, the standard one. And you can see the detail here. It was made from 2 parts. One was fixed to the timber column in a factory. Another one was fixed to the concrete substructure on site. There was a shear lock, and it was fixed by chemical anchors, and together it was joined together using a pin. On the right, you can see the original shop drawings of those two parts. So how did I design this connection 6 years ago? Unfortunately, in that time, we didn't have IDEA StatiCa because it was at the beginning, and yeah, now it's much more further than it was, but our company didn't have it. Fortunately, TAROS NOVA has it now, so they can do it what we are doing. We are showing you right now, so they are optimizing like we do. We will show you. So going back to my original design, I used a couple of spreadsheets. On the right, you can see a snip from my spreadsheet for pin design. I used also like some spreadsheets for the calculation of the plates, like plate in bending, plate in compression, just as calculating the stresses. Yeah, and it wasn't even a part of the document because it's just small, simple tools. In the middle, you can see the Hilti report from Hilti Profis. I used it to design anchors, and on the left, this is just a table to design self-drilling dowels, because this top part of anchoring is connected to the timber column using self-drilling dowels. And just get the force, find the resistance in the table, and get the result. So as you see, I had many tools. It wasn't like a complex check in one, and it took some time. And also I didn't have like a tool to optimize it, so I took like the idea of architect, modified slightly, and designed it like the thicknesses of plates to keep some safety for myself. I don't want to be I don't want to design something unsafe. So, but now we can show you how this connection can be designed using IDEA StatiCa, and then we can see if there is any space for optimizing and saving material. So it means money. So Adam, it's yours now.
All right. Thank you, Jan, for your splendid introduction to your project. I'm just going to take the presenter and show you my part. Okay, should be able to see starting new project in IDEA StatiCa Connection application, and I'll guide you through the whole modeling of the detail of this pinned anchoring. So I'll start with the blank one. I'll use Eurocode and 355 of the steel grade. And I will do this pretty quick because Jan naturally wanted to show off with his project, and it took a lot of time of our time scope today. But I'll try to point out a couple of hints for you that you can use during your workflows and modeling your connections. So some tips for you. So this is the blank project. I will start with adding a member, and that will be the timber one. This is since the version 20.0. Here in the tab, just click on the timber sections and choose the simple rectangle and just input the dimensions. For the, I'll just rotate it to have the column shape. And for the material of the timber, you can find here. There's by default some, let's say, basic timber material. This is something about the C20 construction timber from the code. And you can, of course, edit it here or add some yours and do work with this just as any other material within IDEA StatiCa. Okay, So that's pretty easy to input the timber column or the lower part of the frame. And now what I will do is hide this one so it would not overlap in the 3D scene the main detail that I'm going to model just right now. I'll start adding a stiffening plate. That would be the base plate of the detail. By default, as I added first the timber, the plate will be made of timber as well, so I have to switch it to steel. And I will just input the dimensions of the base plate. Here it is. Now I'll continue with modeling the ribs that are connected by the pin. For that, I'll just copy the operation, and that is the first, let's say, hint for you today. I will use import of DXF shape of the shaped rib. So you choose the polygon here in the stiffening plate operation and click on DXF, and that allows you to browse for some DXF drawings. Now I want to show you how to even prepare such a DXF for the import. So I'll jump to the drawing in AutoCAD. That is the actual drawing of the detail of the lower rib and the base plate. And I'll just grab the shape in here, make a copy of that in a separate drawing, because that's easier for me. And now what I have to do, because this is now a connected polyline, what I have to do for the import is to explode the shape to single lines and curves. Now just save it to the desktop. Let's say plate number 1. Okay, and I will close the drawing so it becomes able to be read. Now I will read it, find the file, read it by IDEA StatiCa. It loads the shape. What I have to do is click on one of the lines, say this is the one I want, click consecutive, that joins the whole shape, and click outline, which creates the 2D plate. Now just OK, and I've got a plate in my 3D model. Now I can just change the thickness and rotate it and put it in the position according to the project geometry. Cool. Just make a copy of that for the other side as well, and I'm done with that. Now I'm going to model this lower stiffening part, or stiffening box. So another couple of plates. So I'll just deal with this by copying these plates and positioning them. So this will be again just simple rectangle. And another hint for you maybe is that you don't have to input this in space with origin and joint, but you can use or take advantage of already input plate or member and assembly the plates on this already existing plate. So I'll take advantage of this. I will just assemble this box on the base plate. So the plate is SP1 and will be rib and the rear side, and Now I'll just help myself positioning it like this. It creates the weld as well already, so I didn't have to use another operation for welding these plates together. I'll just change the thickness of the weld. Okay, that's good. Copy this one on the other side as well. Just change the direction or the side of the weld, so it's outside of the box. Cool. Another plate is the upper one, the cover of this box. Here I'll change thickness and dimensions like this. Say the plate that I want to input on is this SP2 rib, and this will be now front. I'll just put it in the right position, right? And the weld is of size of 3 millimeters. Now I have some overlapping here and some missing welds. I will deal with this adding the cut-off plate operation. And this is maybe or definitely better in case you want to optimize a detail later to use the P-cut, because that would, you know, in case you modify position of the plates, it will still keep you the cut and the weld as well. So you don't have to redefine those operations later. So just simply pick the plates, set the weld, and that's it. And I will just copy this operation and add the weldings to the other ones as well, like this. These plus and minuses means the back and front of the plate that you cut and you cut by. And of course, you have to switch the position of welds as well. So I'll just copy this operation for the others to create all the welds all around. Now the same for the other side. So just like this. Just pick the right plate and pick the opposite welding, like this, like this. Oh, this one missing. That's this one and this one, right? Okay, so I'm done with the lower part and now the upper part. So I'll make a copy of this plate, and that will be the supporting plate of the timber column. So this one is of thickness of 20 millimeters and has slightly different shape. And of course, it's shifted vertically like this. And on this, I have to add now 4 ribs for the connection. So again, I'll use the DXF import. I have already prepared the upper plate, DXF as well. So just quickly like this. Again, position, thickness, and rotation, and it's in the place. Now, make 3 more copies of this, like this, and this one is -40 now, and of course +40. Okay, now one of the next things is to weld these together. So again, I'll use a P-cut operation. Just pick those, change here. I'll use double fillet welds, size of 6 millimeters. Now, again, 3 copies of this P-cut for each plate. That's right. Now, next thing is to add the pin to connect all those 6 ribs. So for that, I'll use a bolt grid operation. I'll pick the grade and the size. And here I can define how many plates are connected by this operation and just pick them like this. In the 3D scene, I have visual control as well, that all the plates become orange and they are well connected together. And of course, just shift the bolt or pin to the right place. Good. Now, one of the very last thing is to connect those plates and add the concrete block to create the anchoring. So I'll just weld those 2 plates using the weld operation now to show you the other option, how to weld things together. Here, if I switch to transparent view, by default, I've picked the edge index number 1, which is this one, the sliding one, and I want to connect edge index number 42, of course. You can see it's in position. I'll choose double fillet welds, size of 9 millimeters. Now, of course, copy for the other side as well. And let's add another operation, how to model the concrete block and the anchoring. For that, that's another tip for you. There's an operation base plate, but that creates another base plate as a part of this operation, and we've got already one modeled. So I'll use the bolt grid instead. And this provides options to not only create bolts, but also contacts and anchors as well. I'll choose anchors and just pick the SP1, the base plate, and just define the anchors. So those are designed to be 8.8, size of M16, length is 225. Of course, positioned in the corners of the base plate, like this. The block is created within this bolt grid operation, so I'll just modify its size. If I input here the offset and the depth, I've got a solid concrete block, and the offset now is 860 millimeters from all 4 edges of the base plate. Now there's another hint or trick for you. If you input more values here, you can define offset for each edge of the base plate, right? So now I've made it a bit wider, so it's now rectangular, having the same dimensions in both directions. Another thing is the shear force is not going to be transferred by friction because it's quite big. So there was the shear lug designed by Jan, and the shape of the shear lug was HAP 100. length is 130 and it's rotated. If I zoom in, show you how it looks like, rotated like this, and of course welded to the bottom of the base plate like this. One last thing regarding the anchoring is that there's a mortar joint for the standoff made of 25 millimeters. Okay, now this is looking already pretty good. Now the last thing is to connect the timber frame and this plate. Okay, for that, I'll just take a look which number of this plate it is. It's SP7. I will turn on the column, which will hide the whole detail, but just for a second, because I'm going to cut the column by this SP7 plate. So it looks like this now. And now to connect these two, the steel plate and the timber member, there are two new operations regarding the timber structures, gusset plate and connecting plate. I will use the gusset plate operation. And here, what I have to define is number of members and which member is it. So it's the M1, of course. And now I'll just define the details of the operation. It can be, this gusset plate can be enclosed, it means on the surface of the column, or inserted, that means cut inside. If I switch to transparent, you can see it inside the timber. So this is what was used, and I'll just play with this a little bit, make two plates instead of one, and shape it a little bit. Change the thickness, change the material to steel one, of course. Change the bolt to M12 now. I'll show you in a couple of seconds how I'm going to change them even more. I'll just position these bolts in the rows and in the columns as well, like this. Now it looks much better. Once again, transparent view, you can see the steel plate cut inside and connected all together with the bolts, with the timber column. Now, I was talking about the bolts. I've chosen a standard M12 steel bolt with washer plates and so on. But as Jan mentioned, the dovels were used instead, of course, to connect these two materials. And I'm going to model them or change them or edit in the material tab. How I'm going to do that, I'll pick the M12 that I've chosen for this connection and edit this bolt assembly, and I will edit the name first. These are the WS7 dowels, and I'll edit here the geometry. Okay, so I've got this in my list of these dovels characteristics and details. I'll just input it here, simply turn off the washer plate or the washers below the nut and the bolt head, and save this I'll call it WS7 timber. And you can see here it's on the list in my library on my computer in my IDEA StatiCa, so you can use it anytime when I'm going to model again any timber connection. So I'll go back to design and check how it looks within the operation. It's here. You can see it in the 3D model. It looks very different now. I've got these small dowels inserted in there. Okay, well, that's all regarding the modeling. And the last thing is to set the load effects. What I'm going to do is input the loads that Jan used for his design, and what he used was the extreme envelope from all the combinations that he had. He just picked the most dangerous force here, and the value was of the compression was 385, and also the most worst shear force he had within his load combinations, and put them together into one load effect to code check the detail. The other one was for the tension. Was just small, of course. That's just because of probably the wind load case and combinations. Now, this approach is okay for the analytical when you don't have any better tools and you don't want to, multiply all the process of code checking, as Jan showed you, using his Excel sheets and his paperworks and all other tools. But now, having IDEA StatiCa, of course, the right and the best approach is to import or input the real load combinations with the right forces within the load combinations, because this is, of course, leading to overkill the design, because you're using the combination of internal forces that are not going to occur, never. Right, but let's stick to this one for this time, because I want to compare my model with Jan's, let's say, estimation, if I can call that. And I'll do one last thing here, because if I turn on the wireframe view, you can see I have some movement in the bolt, which is of course not going to be there. So I have to switch here from nodes to bolt forces. That makes the zero moment in the bolt or in the pin. And also I change the model type to restrict the moments, because there are no moments, and keep it like this. Okay, and now I'm ready to calculate. What I want to do is calculate also buckling, because I'm afraid of these rips if they will not lose stability. So I'll go to check, and I can run the buckling analysis in here. So to save some time, I've done this already with the same model that I've prepared before this session. So I'll just put it in here and show you how we're doing with the detail. And for Jan's sake, we are all fine. The detail is safe. We passed the code checks. You can sleep well, Jan. we have passed all the code checks. Everything's green. Got one yellow weld in here. So let's take a look what output we got. Now, let's say for the timber, it's still quite limited. Well, to be honest, we're at the beginning with the timber, but we're going to develop further more features and functions. So for the timber, so dovels here, they are not code-checked within IDEA StatiCa Connection, but if you can read the forces and just code-check them simply at side. Now, about the buckling I was interested in. Let's take a look how the buckling performs. I'll turn on the mesh and deform shape. Now we can see the first buckling shape with the factor of 4 that takes place inside the timber. That only means that this needs a bit more development in our application because there will be no buckling, of course. But that at least provides us information that I have no buckling in my detail in the steel plates. Let's take a look on the second shape. Again, buckling in these connecting plates or the gusset plates. So I can go further and further to find finally the fourth shape is buckling happening in the ribs. And when I'm reading the factor 21, that means I'm pretty safe and I don't have to struggle or even calculate or analyze the buckling at all, because this is pretty fine. The factor is so high that it's very, very safe. Okay, well, that's it from my side now. I'll give presenter back to Jan.
Thanks, Adam. So I'm happy that I designed it safely. That's of course the most important thing, even with my limited tools. But let's move on and let's ask if we can optimize this detail. Because in my original design, I used plates thicknesses from 10 to up to 25 millimeters, and the total weight of steel in one detail was 152 kilograms. And I can see in this stress diagram that there may be a place for optimization. Probably I will keep the shear lug as it is. It's quite red, but we can focus on other plates. So Adam, can you please just try to optimize it? Keep the idea of the plates. Don't change any shape. Just focus on the plate thicknesses if there is any space for savings.
All right. I have already something in my mind, of course. Let's take a look. Let's take a look about the optimization process in IDEA StatiCa Connection. That's one of the most strongest parts of the softwares that allows you to very easily, simply optimize anything without, making any struggles or errors in the model. It's very easy to edit anything in IDEA StatiCa Connection, and that's perfect for the optimization. And I mean, poor Jan at the time that he didn't have IDEA StatiCa in his office, he didn't have probably time to optimize and no tool to optimize and even no, let's say, mindset to do the optimization. But with this tool, I'll show you how to do this in 2 minutes. How to save material means save money and save your time as well. So Jan could have spent his afternoon with his wife and kids or in a bar at that time, I would probably say. And
Right.
okay, I'll just focus on optimizing the steel plates. We can optimize the bolts, anchors, pins, welds, anything. So let's start with the base plate. I could see in the analysis results of my model that there are big reserves in the stability or capacity of these plates, so I can make them thinner. And so I'm going to quickly go through those plates and make them thinner and play a little bit with their positions. So 15 instead of 25 or 20, that means I have to shift it a little bit upwards. That's the base plate. Next, the lower ribs. 15 instead of 20. You can see this got just modified according to the shape, so I'm not losing any weld or anything here because I used cleverly the P-cut operation. Now 8 millimeters instead of 12 here, here, and here. That's for the lower part, and for the upper part, the so-called base plate 12 instead of 20. Getting gap here, so I have to shift it for these couple of millimeters to get the connection again back in there. And the ribs now 10. Let's try 10, and also I'll shift them a bit to -72, and this 4 millimeters towards. Okay, like this and like this. Well, that's it. So it was like 1-2 minutes of somebody would call that a gameplay, and now I can run the analysis again with the buckling as well, because I'm getting the thinner ribs now, so maybe that's a danger of buckling occurring in there. So let's see the results. Again, already calculated. Voila, all the code checks very well passed. We are still on the safe side, and let's say pretty safe. Still, we've got some capacity left. Let's see about the buckling. Again, I'll turn on the form shape and see the factors here. So we've got number 1, 2, 3, those are ore and the gusset plates inside the timber that are not going to happen in reality. And as you remember, it was number 4 happening in the ribs. The same in this optimized model. The factor was something about 25, if I remember. Now it's 90, which is still pretty safe, far above the recommendations of the limit. When should I deal with buckling or not? So that's a pretty good job. We've optimized this detail, and now let's see what has Jan calculated regarding the savings.
Thanks, Adam. So there was a big space for improvement and for the savings. So let's calculate it. Yeah. So what we have now, we've changed the plate thicknesses from plates 10 to 25 millimeters to 8, from 8 to 15 millimeters. and the overweight of one detail of the steel parts in one detail are reduced from 152 kilograms to 112 kilograms. It means we saved 40 kilograms of steel just in one step. Maybe even you can play a little bit more with it, yeah, but I am quite happy with this design. You can see here in the stress diagram that the stresses are really increased, but maybe there's still some improvement. I said we have 12 frames. It means 24 anchorings. There are also some modification which are connecting the steel rods, but the savings there would be even higher. But let's assume we have 24 of those details, and in such a case we saved 960 kilograms of steel, almost 1 ton of steel. So the unit price for steel varies, and it depends on the region. But here in Czech Republic, we are assuming for the whole product, like welded parts together with the zinc coating and everything, like the price is €2.60 per kilogram. It means that we saved 2,500 euros optimizing this one detail. So Adam spent half an hour or 20 minutes checking the original design. Well, if I remember, it took me a couple of hours to check it, and I didn't have a time to to optimize because I have another details. But he spent extra 3 minutes to save 2,500 euros. It's quite good, Adam. Don't tell my former boss that I could do this job.
Fine.
Good. So, so it's really good to focus on some details. If the details appears multiple times in my structure, it's worth to optimize it. If there is just one detail, the original design weighs 8 kilograms and I can save 2 kilograms of steel, probably is not worth to focus on this. So it's up to you. You are the engineers, and everyone can just focus on the optimization. And in the whole structure, I would pick up another details like the main assembly joints. I believe I could find savings there as well. So overall, I can imagine savings in the whole project like 5,000 euros. And I will save time, of course. We are not talking about time savings of the design, only the material savings, which is quite good. So I think the optimization using IDEA StatiCa is worth, and the time spent on this it's worth as well. Okay, so it's everything from my side. Thank you very much, Adam, for showing me how to model and showing everyone how to model such a complex connection. And I will give a word to Jana.
Yes, thank you guys. It was very interesting. And before we close this webinar, just let me ask you to fill one more poll. And this poll is connected to new functionality of IDEA StatiCa Connection. So we would like to know which feature would you like to be implemented in IDEA StatiCa Connection. You can choose multiple answers, but please select only those ones which you really think is useful for your everyday job. So it can be either code check of pins, or check of bolts in timber, or the check of fire resistance of the connection, or fatigue. Or maybe you think that IDEA StatiCa Connection is perfect at the moment and you really don't need anything more. So please use this poll to let us know. It's really useful feedback for us to know what the users really need. Okay, I will give you a few more seconds. I can see that this poll is more interesting for you than the previous one. I can see more than 80% of you voted at the moment, and I will close it. And let's have a look at results. So I'm quite surprised that some of you really don't need any additional functionality, but for the rest of you, you can see that the most useful feature would be the check of bolts and in timber, and then the fatigue and pin check and fatigue, and then the fire resistance. Okay, thank you very much. And now let me continue with the questions. So I have one question for you guys regarding the code check of pins. It's very common question. So can IDEA StatiCa code check the pins?
Well, this question goes to me, I guess, because I forgot to mention that during my presentation. Sorry for that. I used, as you could see, I used a bolt to connect those rips, and not a pin. The thing is that you can model the pin by modifying the bolt geometry dimensions. So it would look like a pin, but the code check is done for the bolt according to the code, right? And there is not yet implemented the code check for pins, but it's already in a development plan for future versions of IDEA StatiCa. The problem is that the analytical model of the finite elements is very different from the bolt. The pin works in bending and so on, so it has to be developed and verified further. But there is a simple workaround to input a bolt with the geometry properties and material properties of the pin, which is easily editable in IDEA StatiCa. Analyze the detail and then just read the forces, the resulting forces on this bolt, and do the simple code check of the pin at side. Yeah, that's
okay.
it.
Okay, thank you, Adam. Great. So we are almost finished, but before I close this webinar, I will tell you a few more things. The first is that please fill the short survey after the webinar and let us know if this webinar was useful or not, or what topic would you like to see next time in our webinars. Of course, the recording will be available in few days in our support center and on our YouTube channel. You are welcome to download the free trial version of IDEA StatiCa to try yourself if it's useful tool for you. And of course, if you want to know more about the application, about the documentation, more tutorials, more verification documents, or just to find out some new features in new versions, please go to our web and there open the support center, and it's full of documentation for you. The next webinar will be the very popular release webinar. IDEA StatiCa 20.1 is almost done, it's almost baked, and it will be released in October. So come and see what new feature it offers to you. And it will be the October 9th. And the last thing for today is maybe you know Tekla Developer Award. If you use Tekla, or maybe you don't. So we would like to let you know that we also compete in this competition. This competition is done for any company who develops any plugin, BIM plugin with Tekla structures. And IDEA StatiCa was very successful last year. We ended up, I think, on the second place. So today, this year, we compete again with our new functionality, which is called IDEA StatiCa Checkbot. I will not tell you much about this because it's something that will come in, hopefully in version 21. But at the moment, you can have a taste of what will bring. It's the application for automated steel connection design and automated export, loading and code check in one go. So we think it will be a really useful and really successful plugin for you. So if you want to find out more, please go to the web page of Tekla. You can see on their web page tekla.com there is this BIM Awards, and you can find there the checkbot page of IDEA StatiCa. Play the video, find out more. And that's all. That's it. We are done for today. Thank you very much for your time. We really appreciate our audience to come back, and see you next time. Goodbye.
Thank you. Goodbye, and have a nice day.
Enjoy your day. Bye bye.